Om Swastiastu. My name is Putu Januartha Prayoga Putra. I'm from the Udayana University, and today I'm gonna presentation about heat treatment non-ferrous alloys. It's for material of metallurgy. And now I'm gonna to go to the chapter 40. The main reference I use it is metallurgy for the non-metallurgists. Next, the content of chapter is have 8 content, as you can see. The next first is now is the first opening is the heat treatment and non-ferrous. Non-ferrous alloys are heat treated to tailor their property for the a variety purpose, including aiding in the recovery by reducing install stress, promoting diffusion by distributing existing alloy element, promoting new crystalline grains formulation, promoting grain growth, dissolving phase, producing new phase by partition from solid solution, altering surface chemistry by introduction of foreign atom, promoting new phase formation through the introduction of foreign atom. Heat treatment also is used to strengthen some non-ferrous alloys. Strengthening of many non-ferrous alloys by heating treatment typically involves one of two metallurgical principles: precipitation, hardening from the fine dispersion of second phase, precipitation that form in a unstable partial single phase alloy, as in Dr. Williams' mysteries with aluminum copper alloys. Two-phase non-ferrous alloys such as titanium-based alloy and high zinc copper zinc alloys. Stress can be obtained with a mixture of a two-phase comparable quality, unlike the two-phase structure developed in the precipitation hardening, where the precipitation is minor component. Next, some of the common non-ferrous alloy that can be hardened through heat treatment include: first is solution-treated and aged aluminum alloys, such as aluminum copper alloys. Solution treatment and aged cobalt. Solution treatment copper alloys such as beryllium bronze spinodal hardening alloys and other hardening alloys. Quartz hardened metastatic copper alloys such as aluminum bronze, nickel, aluminum bronze, and some copper zinc alloys. Solution treated and aged magnesium alloys. Solution treated and aged nickel alloys. Solution treated and aged titanium alloys. Next, first material is the recovery and recrystallization annealing. Annealing is kinetic term used in the denotation of a thermal treatment process in possession of heating and material to aim temperature and holding a shocking heat from a surfacing length of the time at the temperature, following by cooling at a suitable rate. When the annealing is performing for short periods of the time at a low temperature, the hardness of a cold wafer alloy remaining relatively constant. This initial state is referred to as recovery annealing, like a picture 40.1. Picture 40.1. The next. Some properties do change during recovery annealing. For example, The electrical resistance of an alloy is typically resisted by cold working, but can be recovered before alloying has a significantly effect on hardness, like a figure 14.2. Figure 14.2. Next, extent of coolant work. For example, an excellent amount of cold work period alloying lower than a precursor temperature, like a figure 14.38. There are also approximate relative between melting temperature and crystalline temperature, like figure 14.3b. This is 14.3. Next, the microstructure change that occurring during alloying installation in the figure 14.4 during assembly is designated in the sublimation bands. Although this effect is not permanent. As you can see this picture of 14.4. The next, the second material is heat treatable aluminum alloys. Wrought and cast aluminum alloy are commonly designed by a series original development by Alcoa. The series certification aluminum alloy by particular alloying element. Then, as you can see the table 14.4. This is table 14.4. The next, some approximate crystal temperature are shown in the table 14.3. Following the recrystallization, the energy of the alloy is increasing ordered by adjustment in the grain boundary area by growing curve. And this is a table of 40.3. Next, rock element table aluminum alloys silicon copper aluminum copper like 2XXX series. The aluminum magnesium silicon series is 6XXX, and the aluminum zinc is 7XXX series. And the aluminum lithium alloys of the 8XXX series. There's alloy achieve a higher level static tensile strength, but with less one improvement in figure reduced. As you can see in the figure 14.5. Next, 14.3 cobalt alloys. Cobalt is useful in the application of the make of its magnetic property, corrosion resistant, wear resistant, and or zinc at elevated temperature. Biomedical application is another important use. The initial biomedical application is cobalt-based of cobalt-based alloy are in the dental field, and early evolution as the alloy showed an excellent wear resistance, corrosion resistance, biocompatibility, and mechanical properties. When used in the vivo OS orthopedic implants, the wear resistant cobalt alloys, for example, are SLD, GO, GRVW, and C. Quaternary series. With a chromium provided strength and corrosion resistance, the solid resolution in the application of oxidation as a chief component for formal during alloy solidification to extend provide additional solid solution strength. Alloy for a high temperature strength, including a number of cobalt alloy. Consistently, all commonly important high-temperature cobalt alloy are solid solution strength. Yet, in the past, there were many attempts to develop edge-hardened cobalt alloy. Next, edge-hardened cobalt alloy including 2CONE, HI, CR, and MO. Alloy for the corrosion resistant application, there is alloy MP335N or UNICR 335, which is a cobalt-based component of 35% NiC, 20% CR, and 9.75% MOH. Then balance cobalt. Following presence of CO3 MOH form at the temperature burned in the MP35 and alloy during edge hardening. There are other edge hardening alloy is nickel rich alloy is combination of 36% CO, 90% CR, 7% MSO, and balanced nickel. the difference of their maximum operating temperature. The MP35N alloy is useful up to 4000 degrees Celsius or 750 degrees Fahrenheit, while the MP15 159 alloy maintains the height set index approximately 600 degrees Celsius to 1110 degrees Fahrenheit. The cobalt tungsten and cobalt aluminum alloy system process in the alternating the formation of alloy temperature phase are inter thermophores unable to heat treatment. The alternately alloy confirmation can be used in cutting tool and in operation temperature up to 800 degrees Celsius to 1450 degrees Fahrenheit. Next, the next material, the next chapter is 44 copper alloys. Copper can be hardened by a solid solution alloy and by working hardening. The commonly used solid solution alloy element instead of expression order of the intereffectiveness are zinc, nickel, magnesium, aluminum, tin, and silicon. There are two general types of heat treatment usually in the harder copper alloys. They are often by high temperature alternating and hardened by lower temperature precipitation heat treatment. Those that are hardened by switching from the high temperature to metallizing by concentrating reaction. A list of selection rough copper alloy composition and their properties given in the table 14.5. In the table, the alloy arranged in their common alloy group, the copper 99.3% MiCO, higher copper is 94%, it's 94% MiCO, brass is COZM, and bronze is COSM, and COSM, COAR, COSI. Copper nickel and nickel silver is CONE and ZL. Next, this table is shown. Next, the preparation hardening copper alloy. Each hardening mechanism are used in the few but operation copper system that including each hardening vanadium copper alloy, also sometimes referred to as vanadium bronze. It in both graph is UNSG 70,000 to G 70,530 and cast is C 82,000 to 82,800 composition. X hardening aluminum copper alloy is G 8,400, G 8,200 and G 8,400 that contain 0.4 to 1.2% CR and the production of an array of pure chromium purification and disposal with purification when age hardening GUNI is I. Also G 64,700 and G770,250 that are signed by application of an Ni2Si intermetallical phase later picture 14.6 picture 14.6 this picture. Next, table 14.6 is summary a typical heat treatment for the some hardening copper based alloys. Copper alloy hardening by elevated temperature treatment rather than abrasion temperature. Again, as in the case of so-called natural, again the some aluminum alloy as the superstructure solid solution processor through the preparation cycle. Hardness ensures that there's a peak followed by the reduction in the hardness with time. And this is the table 14.6. Each hardening copper alloy can be thermomechanical processed by provide unique combination of distinct formality, electricability, softening resistance, and sterilization resistance. As a sample, the solution treatment by beryllium copper alloy is performed by heating the alloy up to a temperature slightly below the solid solvents. You can see under picture 14.7 to the small maximum amount of beryllium. The rapidly reducing the material to the room temperature, the beryllium is supposed to turn solid solution. This is the picture of, you can see, and next. Preparation hardening itself, the class process is not planned and ground where the purification of the composition must be as further grow in the top region like in picture 14.HA. In purification below the crystal level and in nuclear formation do not grow bottom part for picture 14.8H. In constant spinodal reaction involving continuous or homogeneous clustering or unmixing of the atom into a two-phase structure by spontaneous growth for small composition friction picture 14.8 B. And this 14.8 is H and it's B. Next, spinodal structure are the characterized by what has been described as a movement of 3D structure. They are particularly occur preparation of crystallographic reaction, providing a brief schematic present in the 2 or 3 direction. The chemical segregation accordance of very small from level scale and require to use of the electron microscope to be discriminated. Like a picture 14.9. The microstructure that developed during spinodal conversion has a characteristic product that in the typical 2.5 to 10 Newton meters or 25 to 1000 each mechanical system. These pictures. Heat treatment of aluminum bronze. Aluminum bronze including 2 types. First is single phase aluminum bronze alloy with an FCCH phase crystal structure. 2-phase aluminum bronze that contains in the FCCH phase with either a body contract could be like HBCC or B. Solid solution phase at high temperature or R. HL4CO9 and preparation set Y2 at lower temperature like a picture 14.10 is a picture. And then next, like standard steel Fe0.77 C. If you have alloy combination of CO 11.HAl is lower cooler from the B phase that is microstructure from a distant smaller structure like a picture 14.11 much like perlite in steel. This is a picture if you can see. And next it, the microstructure of B has the different step like plate like microscopy and then like a picture 14.12. Each hardening is done with the 2-phase aluminum bronze containing 9 to 11.5% HR as well as nickel bronze aluminum bronze with 8.5 to 11.5% alloys. This is the picture. Next, about table 14.7 give typical tensile property and hardness of 2-phase aluminum bronze after various states of the equipment. This is the tables. You can see this. Next, Heat treatment of the branch is copy zinc alloys comparison various types of brass and long being the great chemical importance. Zinc has a rich HCP crystal structure, so solubility in the copper cannot be complete. However, FCC copper is also close-packed with an atomic size difference by only about 40% with zinc. Thus, solubility is extensive. Picture 14.13. This picture 14.3. The next. Copper zinc alloy also can develop of mesocytic phase during quenching, and important sample is the represented in the CuGNLL. Save memory also like a picture 14.14. Picture 14.14. Next. Copper zinc content is found most commonly world based on this are showing in the table 14.8. Table 14.8. Next. Next material. This next chapter is magnesium alloys. There's composition of occur in many magnesium alloys, but in preparation does not always result in hardening. In many ways, alloy like teach cold range and lattice staining is lost early in the formation of preprestations. Some example of significance hardening that does occur from the preparation including magnesium alloy for alloys like a picture 14.15 pictures. Next, magnesium tritium alloy like a picture 14.16, and this is the picture. And next, and magnesium alloy like a picture 14.17. Next, 14.6 nickel quartz. Nickel is an autosolution former and non-allotropic phase transformation occurs in nickel of the high nickel family of alloys. In heat treating nickel or nickel alloys is crystalline to minimize export to survive in solid metal lubricants and grations or gration form like SO2 or H2H. Factors that influence the selection of number gain the step that the preparation time of temperature including anti-pression surface temperature, design partition size, that combination of strength, ductility, desired, and other factors. Some example again condition for the super alloys are showing in the table 14.9. Table 14.9. In terms of microstructure, the G application has to be rather unique cubic methodology like a picture 14.8C, and the size is determined by again condition as illustrated by microstructure like on a picture 14.18. Let's see. This is pictures. Next, the chapter is 14.7. Titanium alloy. Titanium and titanium alloy are heating treatment by order to reduce stress development during fabrication or stress leveling, produce an optimal combination of ductility, mechanability, and dimensional and structural stability in a link. Increases strength, solution strength, and again optimize special properties such as further toughness, fatal strength, and high temperature grip strength. Like iron, titanium is application diamond. Titanium has a HCP crystal structure called alpha H. Placed at a temperature below 805 degrees Celsius or 1825 degrees Fahrenheit. When the temperature is pure titanium reach in the 885 degrees Celsius, called the transverse temperature of titanium. The crystal structure change in the BCC structure. The high temperature BCC structure of titanium is referred to as the B phase, with the presence in the temperature up to melting point. Next, Following element either rise in the lower the temperature or for the L to B transformation. So alloying element in the titanium are classified as either a stabilizer or the B stabilizer. The I stabilizer dissolver primarily in the E phase expand this field that thus raise the H or B status. Figure 14.19H beta stabilizer reduced at H for B transfers and stabilizer that B base are there are two types of B stabilizer. First is isometric B stabilizer that is formed by binary system like a picture 14.19B, then beta stabilizer that favor formation as a B expression like a picture 14.90C. This is picture and this okay, as you can see this. Next, the combination of titanium alloy classified based on the type of the amount of the alloy element as with respect to the formation of the ether, the base, or the B base. Summary that some titanium alloy is listed in the table 14.10. In the table 14.10. Next, primarily in May is allocated or equalized depending on the prior position and heat treatment. For example, three different molecular qualities of the family in alloyed titanium are seen in the microstructure like a picture 14.20. This picture. Next, the amount of the base and comparison with secondary H become are more predominant in the aged alloy, such as TH6Al and 2SN, 4GR, and 6MOH. Like a picture 14.20. This picture 14.20. When those alloy are acquired from the heat treatment temperature of 870 degrees Celsius or 6000 degrees Fahrenheit, the microstructure contain big base dark that primarily H is white and in the picture 14.21b. For example, more than primary H become a B during the heat treatment. The and of the B is the transformation into during cooling. There are secondary application in the picture 14.21b. A small white needles within in the regions of B or dark when the heat treatment is done is still high temperature. More family is so further and more solidification result in pre-transformation during cooling like a picture 14.21c. Next, depending on cooling rate, the areas of second or secondary H phase have different preparation for the shape that are described as last smaller plate like acicular with mass tinted, serrated, or mestensitic. For example, picture 14.22. So it is microstructure of the alloy that are something at 1177 degrees Celsius to 2150 degrees Fahrenheit and cooling in the three different rate. H is smaller than plate like a crunch occur with a slow cooling like a picture 14.22H, while when acicular abrasions occur at a high cooling rate like a picture 14.2022.22b. This is 14 picture. And next, beta stabilizer lower the EPS temperature as illustrated in the picture 14.23. For the variation of vanadium content added to TH6 composition. This is pictures. The next, high energy temperature, dilute and vanadium concentration, typical temperature of national information by acquiring or showing in the figure 14.24 for some common titanium alloy. Sometimes that is difficult to distinguish between each Mesin site and aquifer H, although aquifer are usually in the less well definition that has covered rather than straight lines. Martin states in the titanium and titanium alloy typical occurs as flat templates. You can see this picture is 14.24. Next, this comparison of retinal B or Mesin site if its form is the basis of heat treating titanium alloy to high stage. The time temperature combination select depending on the requirement strike. A summary of again time and temperature precision in the table 14.11. This is the table 14.11. The next. Again, they normally carry out the range of 425 to 650 degrees Celsius or 800 to 1200 degrees Fahrenheit. Figure in the picture 1425 showing in the some general feature of the gain process. This is pictures. The next. Titanium H alloys, unlike the HB and the B alloys, the H and near H titanium alloys cannot be strengthened by heat treatment. This is an illustration in the figure 14.28, which it displays there four different heat treatment of the H alloy: HBNR, 1MO, 1V. Operation is done from four different phase regions, followed by a gain. When the alloy is acquired from the region above the near the B transition position of B, okay. H and B at the middle diagram. The microstructure contains the more secondary H and also mentioned in the figure 14.28H. This is 26H. This picture is the next. The heat treatment of 1065 degrees Celsius to 950 degrees Fahrenheit is above the B's census and rapid cooling result is microstructure that is a circular edge and Mesin site, although the structure is not as depth-light. It does provide more creep resistance like a figure 14.27. These pictures. Next. Titanium HB also they are most common and the most versatile of the three types of titanium alloy. Phase composition, size, and distribution can be manipulated by heat treating with its content limit and a chain of specific property or the strength of the range level. The typical heat treatment is summoned in the table of 14.12. This is what table. Next, heat treatment is of a HB alloy within a B range cause in the significant loss in the ductility. The B transition is the action. The resistance property of the HB alloy, specifically ductility, are reduced in the figure 14.26, and that cannot be fully restored by subsequential heat treatment. This picture is 14.28. Next chapter is order on non-ferrous alloys. Heat stable silver alloy is furnace metal, including silver, before somewhat similar in copper and nickel. The most important silver alloy are the silver copper type. Copper is added to the test and hardened and the strength of the silver, while its effect is electrical conductivity is smaller compared to that other addition. Coal silver content is 10% Co is the most commonly alloy. Coal silver is 99.9% Eg. All silver alloy and with more than 2% Co can be professionally hardening in question for the approximately 750 degrees Celsius or 1370 derajat 75 derajat Fahrenheit, and again at 250 to 350 derajat Celsius or 475 to 650 derajat Fahrenheit. However, this statement is seldom applied in the commonly expressed of the hardening in spite of difficulties of content with its corrosion and brittleness of the silver copper alloy. Heat treatable gold alloy in the gold alloys which find application in the Januartha setting trend and in the destination general contain silver and copper, and sometimes zinc, nickel, platinum, and palladium. Next, the aquamarine diagram of the gold platinum in the similar of the gold nickel alloy within more than 40% PTR used in the penetrant that iron in the stain are difficult to work and can be professionally hardened as many systems of the platinum palladium based on titanium gold are characteristic by the presence of the terminal phase of the preparation process such as platinum silver, platinum copper, and palladium copper. Heat thermal low mill alloys and PB and ZN. Zinc-based alloy cannot be improved suicide by heat treatment and one commercial concern of such practice. Some hardened lead-based bearing alloy contain their calcium, sodium, and lithium as an effective consumption. After casting, they are edge hardened at the room temperature, attaining their hardness up to temperature of approximately 100 degrees Celsius or 200 degrees Fahrenheit. And that's all the material presentation to you guys, and thank you for watching, and maybe see you in the next video, and thank you so much for watching. Bye.